talk. I'll let Mr. Chetan introduce himself and proceed with the episode.
Sure. Thanks, Sammy. Good evening, everyone. My name is Chetan Kulkarni. Let me just open my slide deck so that way you can just see what. Okay. Can you see my slides? Sammy, you can see my slides?
Yes.
Okay. So good evening, everyone. My name is Chetan Kulkarni. I'm part of the Diagnostics and the Prognostics group at NASA Ames. We are based in Mountain View, California. So that is where you will see most of the Silicon Valley is based, and we are exactly very much in the center of that place. The group what I belong to is a part of the Ames Research Center. So that's where our center is. And we, as the Diagnostics and the Prognostics group, have been doing work into how to keep the airspace safe, and also both from the aeronautics point of view and from the astronautics or the aviation, the astronautics point of view. What we do is we support any missions, long missions, short missions, autonomous missions, wherein we try to evaluate that how the system is going to behave in the future. Because what happens is when the system goes in an autonomous mode, or it goes to a long mission, you don't have access to check on the health of the system. And that's the reason what we have to do
Mr.
is...
Chetan,
Sorry?
your screen is shared, but not the slides.
Oh, really? Oh, okay, sorry. Let me check what's going on. Let me stop sharing this back. Does it look now? Okay, sorry. I thought I was shared. There are multiple windows which come in. Okay, so yeah, that's what we, as I was talking, that what we are trying to do is we are trying to check on help the systems, or help the vehicles, keep them safe, make sure that they are in a healthy state and they are able to perform their mission. So that is the work what we have been doing. The group started in 2006-7 at NASA Ames, and it has been more than 15-16 years, and over the period of time we have looked at various systems. So anything which breaks, that's exactly what we try to figure out, that why it is failing or why it is breaking out, and then try to develop our algorithms around it. And I'll do talk about those methods, and I'll talk about how we are performing that and integrating it with the safety of the aviation space. And even from the currently the work is more defined towards aviation, so the application is for an aviation system, but it can change. We apply it to a lot of other areas also. We have been working on the ISS. There is currently some work what we do on the ISS to help the astronauts on how the systems are breaking down, and can we help them in reducing their workload. So those are the kind of things what we have been doing. So with that background, I thanks the Sammy and the society for inviting me to the talk, and I'm very honored to be here to give that talk. As part of the society, we have a brief a slides deck, which is part of the IMS society. So I'll just talk something about that. Give me a minute. And sorry, my dog is barking. Really, my wife left, and she's not very happy about it, so that's why. But yeah, so we are as part of the DLP lecture series. We are part of the IEEE Instrumentation and Measurement Society. And what we are trying to do is we are trying to look into the field of interest. So mainly it's the field of science, technology, and applications to different instruments, probably medical or any of the industrial applications. And we are trying to look into presenting those as part of the society. The society has several chapters. So if you see, they are into 10 regions, and total there are 55 chapters which are there as part of the IMS society. It supports various chapters. So we have a chapter for funding the program, for development of it. There are a lot of awards, several awards which are part of the outstanding chapter award, depending on what chapter it is. So we have the Type A society, same like what society you are part of. And you can have more information on the chapter toolbox of the society. It also looks into development for women in INMM, a lot of student activities, and I think today's talk is part of that, like the student activities which are going, and I'm very much happy to be part of it and support this. Also, young professionals who are just graduated and who want to be part of IEEE. So how does that work out to boost their career skills and also their network? So that is one of the key goals of the society. There are several conferences which are there as part of the society, and I2MTC is one of the prominent conferences. That's the flagship conference, but under that also, depending on your area of expertise or your area of research, you can look into other conferences also. So there is AutoTestCon, which I have been part of for a long time since I was a grad student. I took part in AutoTestCon. But then there is Sensors and Applications Symposium. There are the imaging systems. So if some of you may be interested in those, please look into those details, and you can try to apply and present at those conferences. There are also publications. There are several magazines which are there, wherein you can, some of the journals or some of the high quality papers, they get published in these magazines, and please go through them, and also make sure that you benefit from them, because there are so many nice works which are presented through this magazines and publication journals, which are always useful to students, and especially depending on your area of research. And also, like today's program, we have the DLP, or the Distinguished Lecture Program. There is always the Faculty and Post Development Awards, dissertation awards, which depend on the area of what you're working on. But please avail those facilities, because that's very important, that the society is helping the students, and students can avail those facilities using the portal, and also the society details, what you can look on the website. But you have undergraduate scholarship awards. There is a lot of contest, IMS student contest, and also several networking videos. So these are all available on the IEEE website, on the learning network. So please avail those facilities. And then finally, we have there are several technical committees. So there are almost 28 standards. I'm part of one of the IEEE standards, which is specifically towards systems health management and prognostics. I've been supporting that for some time. And recently, I'm supporting some battery work standards also, where we are coming up with a white paper. But yes, there are a lot of different standards, and it's always nice to interact with those standards also, because then you get to know, okay, what are we looking forward, because standards come something even before the industry accepts it, or even before the industry is able to come up with their own set of thresholds. So standards always give us a benefit, that what does the industry look for, or what is a generalized approach the researchers and the educators and the industry are taking towards. So that's a very good way of getting involved in standards and technical committees. So I very much encourage all of you to look into those. And finally, there are a lot of awards which the society is providing. We are in the 75th year, and there is a as you can see, there are different categories of awards. So if you fit in any of those categories, please apply for them and avail the facilities. So it's always
Mr.
nice to.
Chetan, sorry to interrupt you. I
Yeah.
think your slides are freezing or froze.
Oh, frozen.
We're still
Oh,
in the first slides. So
oh, really? Oh, that's very weird, because my screen shows the slides are moving. Okay. Uh, okay. Can I? Uh,
we
okay.
can actually see your mouse, but
Oh, really? Oh,
uh,
that's so weird. Okay.
maybe
I'll
you're
stop.
sharing a window that it's not.
Okay. What I'll do is I'll share my entire screen. Probably that's a
Yeah, you
better.
should share your entire screen instead. Yes, this is better.
Okay. Can you see it now?
Yes, we can see it.
Okay.
So can you
And
briefly go over the missed slides and just
yes, 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 sure, sure.
briefly?
So uh, what I was talking about, I'm very sorry this happened, because yes, so we have the chapter support. So what we are doing is we are funding different chapters, and also looking into different awards, what are avail what the students can avail. So this is for all the chapters, especially someone like today's program. And also, there is a lot of work done in the membership development. So looking into women in INM, a lot of student activities, a lot of young professional programs. So those are very important. And I think I would very much encourage for you to look into how can you boost your early skills. Like some of you may be graduating soon. So how can you boost that skills, and can you boost your professional network? So that's another good way for you to interact with new folks, someone who is in the industry. So very much encouraged to be part of the YNP program. There are several conferences which are part of it. So the flagship is the I-Square MTC, but as I mentioned earlier, probably when the slide was not there, but AutoTestCon, which is this third conference. I've been part of AutoTestCon for a long time. I participated as a student there, and it was a nice experience for me, because I could meet someone who is in the industry, someone who is working, learn from them, and also being part of those conferences gave me a good contacts to ask questions, because sometimes you're in your research probably, and you think, okay, can I ask someone question, but these contacts where you come through, or some of the papers what you read, those always help you to get those connections and help you with your research work or your graduate studies or undergraduate studies. So it's very much encouraged to do that, and it depends on your liking. So if you like, you're in an area of probably image processing, so you can look at those specific conferences. Or if you want to, there is a lot of work which is done on automated vehicles or electric vehicles. You can go to those conferences. So please avail the facilities accordingly, as per your area of research and liking. There are a lot of journal publications also. So there is an INM magazine which comes every two months. There is a newsletter. There is a lot of couple of journals which are indexed and through Web of Science. So please avail those facilities. So all the good papers which come through the earlier conferences, what we saw, they are invited to present at these journals, wherein you can yeah, improvise some of the contents of your manuscript, and then you can publish them in these journals. So it's always a nice opportunity from that perspective. There is, from the education point, like today's program, we have the distinguished lecture program, which provides you wide spectrum of capabilities, that what are the different areas you to learn about. So because something, everyone has a new perspective on presenting their work. There is so much of good research going on all around the world. It's always nice to know about that, and then you can tune your work around it. So there is the fellowship award, there is a dissertation award, a lot of undergraduate scholarship awards. So please avail those facilities on the IEEE Learning Network. So you can look at them, and then you can have the website provide more details to you. As I was mentioning about the technical committees, please get involved in these standards. I'm part of a few of IEEE standards, which helps me learn about those things. because the industry is trying to come up with these standards. Why? Because then those could be implemented industry-wide or by other uh, uh, communities, which are research communities. They can use those facilities, and they can adhere to it. So that way, whenever you have a communication between different what you can say, um, industries, they are on the same standard. So like for example, the area what I work in is the Prognostics or the Health Management Society. So it can be applied to automobiles, it can be applied to systems, it can be applied to plant, it can be applied to like complex systems. But if you have a common standard, in either cases, you always adhering to those specific standards. At least you are keeping some basics conform to it, and that helps to understand that if someone is talking from one industry with another, they talk on those standards, and they can have their data being provided in that specific manner. So there are various ways in which you can implement those, but always good to be part of those societies and standard committees. And finally, there are a lot of awards. So as you can see the list, if you fit in any of those awards, please go ahead and submit your nominations. And it's always nice to get recognized for your work, what you're doing, because all of you are doing such a nice work within the chapter, within your university. So please go ahead and submit those nominations for the students and also for the faculty. So so that's the basic of the IMS Society. I thought this is what we are trying to encourage everyone to be part of it. So if you have any questions, please reach out to me, or you can reach out directly to the society, and they'll be able to help you out with the nominations and all the other related activities. So with that, what I will do is I'll start with my presentation for today. Okay, so Sammy, you can see my presentation? Sammy, you're able to see the presentation?
Yes,
Okay,
I can see it. It's in the first slide, right?
Yeah, we are on the first slide. And
Okay.
yeah, so with that background of IMS, we'll start with today's talk. Thank you so much, Sammy. And also what I talked about earlier, a brief introduction about our group and my work. So what we will be talking about is on model-based approaches for fault detection. So fault detection is basically how you detect a fault. Prognostics is how do you see that fault progressing over the period of time. Basically that, okay, I know something is going to fail, and now what's going to happen in the future. Fault detection and prognostics is exactly like the way you go to a doctor. So you feel something is not correct with you. You go to the doctor says, okay, you have cough and cold, and if you take this tablet, my prognosis is you will get better in 3 or 5 days. And that's exactly what happens to machines. You detect a fault. If something is not looking good, you figure out what's wrong with the system. So it's like you go to the doctor, your body is not feeling well, but the doctor gets a diagnosis and says, okay, you have a throat issue, or there is some infection in the throat, or your hand is paining, or probably your head is paining. They will prescribe you the specific medication, and then you get better in the next couple of days. That's exactly what it was for fault detection and prognostics for machines. And based on that, now what happens is, okay, I know something is failing. I know it's going to fail in a certain amount of time. What can I do about it? So that's the decision making of the whole system. Like, okay, it's same like what you do. Like, oh, I'm feeling okay. I can go to office, or I'm not feeling okay. Probably I should not go to office, or I'll stay home back. That's the decision making process. So if you apply that exactly to yourself, that's exactly what we work on, but only in this case, it's the machines part. So that's a very good analogy. I always give it because then it makes it easier to understand what is the work, what we do. And as I mentioned, we are part of the NASA Diagnostics in the Prognostics group. But under that, what our overall goal is, we are part of this the system-wide safety project. So system-wide safety is a innovative solution, which we are trying to assure that it's safe, rapid, and repeatable, wherein you're accessing the national airspace. So national airspace is the airspace on the overall North America. And what we are trying to do is we are trying to keep it safe, but we are also trying to make it sure that as it rises or as it expands, how can it be the safety processes can be repeatable and be applied to everything, not only to a constrained space. The SWS project was started in 2018 as part of NASA's ASOP, which is the Airspace Operation and Safety Program. And it's trying to evaluate that how do modern aircrafts impact safety? Because what's going to happen is now you have a lot of passenger aircrafts, which are the Boeings and the Airbuses, which are flying. But over the period of time, you are going to see lot of small vehicles. So you must have seen that UAVs are flying. There are like this drone which are delivering goods nowadays. So when they come up in the space, that's going to increase the way the space is going to behave. So how do you counter that, or how can you make sure that your airspace is going to be safe? So that with that intention, this program has been developed, and we have been part of it since 2018. I've been very much involved in this part. What we are trying to do is find out different systems, or explore and discover and understand the impact of safety with this complexity, because now you're adding more aircraft. Lot of you must have heard that there is these flying vehicles or flying cars, which is something like the Joby and the Archers and a lot of other systems which are being introduced in the airspace. So when they come in, they are going to do a lot of short flights, and I have a schematic in the later picture to show that. But when they come in, they are going to add more complexity. So with that, when they are able to access the airspace, the expansion of the services to these air vehicles is going to increase very much. And then we have to keep them safe. And what we are trying to do is we are trying to develop and demonstrate these innovative solutions, which will modernize the air transportation and also the global airspace, trying to look into what mitigation risks are there, because depending on if you have a few vehicles, then your risk is low, but if you have more vehicles in the airspace, then your ability to put that risk is very high, because there are a lot of humans which are on board, so we have to keep them safe. So that mitigation risk increases, and that's what SWS is working towards, that how do you keep everyone safe, both in air as well as on the ground. As part of that R&D work, we have been provided with these 4 technical challenges. So one is the in-flight safety prediction for emerging operations. One is the autonomous systems assurance. TC5 is the safety demonstrator, and then TC6 is in-time aviation safety management. So these are some of the technical challenges what we have been provided within NASA, within our AR&D, or the mission directorate, and we worked on these 4 of them. The green, what you see, that's the in-flight safety. That's what we were working from 2018 till 2024. So we worked on it for almost 6 years, and that project has ended, and we are into TC5, and that's the one what you see in orange. So that has moved from green to orange. So green is complete, orange is one which is ongoing. And what we are trying to do is we are trying to develop this concept in the in-time aviation safety management systems, which is the ISMS. I'm very sorry, there are a lot of acronyms what we have, so that's why I do NAS, there's SWS, you will see SFCs, ISMS is another one. So within NASA, there are a lot of acronyms, and they also keep on changing. So please bear with me for those acronyms. But I'm sure these will be the last ones, and then we'll move to more simpler ones. But yes, the ISMS is an integrated service wherein we are trying to develop this functions and capabilities, which is called service function and capabilities, which are SFCs. So SFCs are basically, if you want to know about something system, or you want to address some operational risk, you develop your own. It's like an app, and I'll show you how that app works. So you develop your own module, you connect it to the system or the service, and then the service is able to provide you with whatever information is required during your operation. So those are the SFCs, or service functions and capabilities, what each one of us have been developing to attach to this SWS framework. So our research portfolio, so each research area is designed to proactively mitigate risk, and with future aviation operations enable the modernization and transformation which is envisioned by the ARMD, which is the mission directorate, and what the research areas what are designed to proactively mitigate risk which are associated with that, and also enable the modernization and transformation envisioned by the ARMD. So under these conditions, what we are trying to do is, in these different research areas, we try to mitigate that how the risk moves from one area to another. So in this case, TC1 was predicting the terminal area risk assessment. So terminal area is something once you land or before landing, the 10-mile boundary what is there. So once the aircraft enters that boundary, you are in the terminal area, and that's exactly what happens. So before you actually land on the aircraft, whenever you are within the 10-15 mile boundary, once you land, the aircraft lands down, the aircraft then has to move around a certain area, and then it goes to your the destination, so where you are able to get down. So that's where the terminals are. So that terminals area is also very risky, because the aircraft has to move in a very certain maneuver. They have to be in very specific areas, they cannot hit each other. So that safety is very much critical. So that there was a lot of work done in the last few years on that area. Then VNV for commercial operation, that was verification and validation. So how do you do that? That ended in FY22, and we were recently working on the TC2 and the TC4, and now all of us are moving towards this ISMS for AAM, which is the Advanced Air Mobility Vehicles, which is a safety demonstrator series. What does the safety demonstrator series mean? Is we are trying to demonstrate that on actual flights, actual airspace. So our algorithms actually work on those vehicles, and they are able to give in time assessment of how each one works around. So in the past 4 years, 4 years, each one of us worked on these different areas. Now we are all combining that information together, and then each of our algorithms and frameworks work on these different areas and show that how good it is, and how that can be then brought into the actual commercial application. So that's the transform national airspace with ISMS. So trying to automate it, trying to add more capabilities to the complexity, that's what the research portfolio is. Under the SWS the specific portfolio, what we are trying to do is, how can you improve efficiency of flight? How can you access airspace? How can you expand services? And then try to look into the impact of safety, how to develop and demonstrate the innovative solutions. So how are we trying to develop the new solutions through it? And can we mitigate risk? So this is always, these 4 points are always key for us. So it doesn't matter which SFC or which algorithm you are developing. What we have to look into is these 4 bullet points, that okay, how can this research be tailored towards one of these key points for making sure it's safe, mitigation risks are looked into, and whatever solutions you come up with are applied to it. So how does the airspace look? So in the past, it has been something like this. It was a lot of human centric. It was safe. There was low density, and it was completely human centric. So you have an ATC, which is the air traffic controller. Everyone sits there. They are able to monitor. Each traffic controller is able to monitor like 5 to 6 planes within their scope, and that's what they have been doing. We are moving from that to a digitally transformed infrastructure, where it's a collaborative environment, wherein you are it's tailored to specific services. It's trying to use a lot of machine learning, a lot of AI, a lot of IoT devices, wherein what happens is you have a few aircraft which are already automated. There are few aircrafts which are piloted, so it's a combination of piloted and autonomous systems. And the future is it's completely autonomous, it's completely automated. So that's where we are moving towards. We were in this phase for a long time. We are currently in this centrally digitally transformed phase, but what we are moving towards is a completely automated enabled diversity. And what does automated enabled diversity means? That means different aircraft. So there will be automated aircraft, like autonomous drones flying, autonomous UAVs flying, but also your general aviation, which are the small twin turbo aircraft. There could be some high, like a jet planes, like the Boeings and the Airbuses. So those will be flying. So it's a combination of very much different vehicles, but how do they mesh together with each other? So that's where we are moving towards, and how can that be done? So that's the end goal for us. And when I talked about the diversity, this is what the diversity is. So you have small commercial aircrafts which are flying within very much locally, so which is the low altitude urban area. Then you have urban passengers. So basically what you're talking about is the small UAVs, what I talked, or the UAMs, what I talked about. Those will be like, if you want to go from your main city to the airport, probably it takes like 1.5 hours to reach your main airport, but these aircrafts will take you within 15 or 20 minutes because there is a lot of congestion on the ground, and they'll be flying at very low altitudes, and that's exactly what these aircrafts will do. Then you have the regional air mobility, which are more like your general aviation, your twin turbo, single prop engines. These are small engines. And then you start moving towards more like the commercial aircraft. So these are your Boeings and the Airbuses. But in addition to that, there are a lot of other things which are happening. You have some supersonic aircrafts which are going on. There are some large UAVs which are moving around, which you may not see, but they are in the airspace. So they are already there. There is some high altitude endurance aircraft which are flying. So there are some space launch operations happening. So now with the space operations taking a lot of priority, you would see that every day there are like almost 1 or 2 launches which are happening. They are either going, some satellites is being launched, or some of them are going to the space station. Some are trying to build their own space stations around. So it's a mix. So the airspace is very mixed, and you have to make sure that all of these are constrained in a way that they keep everyone safe. So it's like when a space launch happens, the area has to be cleared out. So wherever the space launch happens, the aircraft cannot be within a couple of 100 miles around that area. So how do you keep that safe? If the president of any country is moving around, they have to keep that space area open. There are some constraint areas which are there. So how do you make sure that, and this is dynamic, this is not static, like, oh, for the whole day keep the airspace completely blocked off. You cannot do that because there is so much things happening. So what you do is you say, okay, for the next 1 hour or 2 hours, this specific airspace is very much constrained, no one can go around it. And that's where then the launch happens, or the president's aircraft is moving around. So those kind of things happen. But the rest of the vehicles, they keep moving. So your general aviation is moving. There are some vertiports in the future which will come, so those will be moving. And now with this recreational UAVs, they may be moving, but they are very much restricted in those areas. So if you look at the picture, you can gauge that how that complexity happens, and how we are trying to keep that, make sure that everything remains in mostly safe environment, and also you're trying to mitigate or lower the risk as much as possible. So what we are trying to do, or what challenge we have? So we have more operations. So more operations is equivalent to more risk, because then you have a more potential for the system to have some issues. With new missions, you have to increase the complexity, because if you have integrate an autonomous system or an autonomous test mission, that's increasing the complexity. And from the sustainability point of view, like how can you reduce your carbon footprint, or how can you reduce your flight paths? So that is putting a lot of constraints, because now I cannot take a very longer route to reach the same place. Can I take a shorter route, which is more optimized, and which will reduce the carbon footprint? Because what most of the airlines require that, because they say, oh, instead of flying like 100 miles around, can I take a shorter route? But if that shorter route is cutting into some other operations, how do you keep that updated? So the airspace always keeps on moving around that, and these are the barriers. So the digital transformation, the advanced air mobility, which is the AAM, and then automation and autonomy. So these are the three main challenges which we have been tackling to overcome this the challenge. And now comes our work, wherein we are trying to integrate into some of these. So what are the complexities in this area? So under SWS, what we have is, if you look at this blue aircraft, so this is one of the aircrafts what we will be tracking. So this aircraft has to move from probably one place, point A, and it has to go to point B, which is a local hospital or a vertiport. It has to carry some medicines, or it has to carry some passenger emergency or medical requirement. But what happens is, when the vehicle is moving, either the passenger may have some issue because it's a medical aircraft or a medical vehicle. It may have some issues, so it may need to diverge. So instead of taking, this is the path which it was assigned, but probably it cannot take this path. It has to take some other route. So the original route was this red marked route, and due to an emergency, probably it has to go through another route. So probably that may happen. So now your route has changed. It may also happen that the vehicle itself may have a fault because the vehicle system has failed. That may be due to operation or some other thing. So should you continue your operation, or should you land somewhere locally, or should you have an emergency landing at a local airport? There could be something like the weather is moving around. So there is a lot of weather conditions which are happening. So there could be those issues. So that's another thing. There could be other traffic which is coming in, like this helicopter, probably it has a path which is crossing the exact vehicle path. So in that case, should you modify your path, or should you update your path? Because these decisions have to be taken within a very a short period of time. There could be a flight which is outside the approved airspace, because there are some, as we talked about, that there are some constrained airspaces. There is an unsafe proximity to other air traffic on the ground, as well as on the on the nearby area. Sometimes, as I mentioned, the vehicle may have some issues. There may be hull loss, or if there is some issues with the battery systems or with the mechanical systems, then you have to land the vehicle. Other things would be loss of control, because probably there is some control failure, and then how do you mitigate those risks? And then always there is weather encounters, as we talked about. So these are the weather encounters which are happening. They may be around it. So when you're flying or when you're moving a vehicle, it's so many different things are happening. So it's very important to know that what is my health state, or what is where I am. That's very important. So the presence of mind, what you talk about when you're walking also, like when you're walking, you always look, okay, is there a pothole in front of me? Is there a stone in front of me? If there is a bus coming from the right side, or someone is walking behind me, those kind of things. That's the presence of mind, what we try to keep here with the vehicle. And in our case, we focus more on the vehicle itself. So this is what we focus on. There are a lot of things happening, but what we focus mainly on is the vehicle itself. Like, is the vehicle safe? Is the vehicle healthy? Is the vehicle able to fly? Is it able to make whatever assigned mission is given to it? Is it able to make it? So that's what our work is. So in this whole complex things, what we always focus on is the vehicle itself. That's it. So for us, rest of the things are there, but we always try to make sure that the vehicle is always healthy. That's what our goal is. So with that as a whole story behind it, that why we do this work, we'll go into the background of how we can go into details now. So we have the background, now we'll go in the depth of it. So I talked about the SFCs. If you remember that, I mentioned that we'll talk about it later. So here is our vehicle. So this is the vehicle what we are flying. On the first layer is the logs, the event logs. We have a ground station which is connecting to the operator. We have some other services. So the FIMS, and the FIMS are basically they are setting up informations or the monitoring system. And on top of that, you have this branch, and wherein there are different service providers. So you have service provider 1, you have service provider 2, 3, and 4. So what are these service providers? They are basically your delivery services, or probably they are a delivery service or a medical service or any other service. That's what they are. So what they do is they keep on providing their information. So this is providing that, okay, what is my dynamic density? DD stands for dynamic density. BP is the battery prognostics. PTT is the proximity to threat. RF is, okay, I'm an autonomous system, but is my RF radio frequency? Am I jammed with any radio frequency? VM is, what is my weather? What my weather modeling is going to do? A GRASP is a very interesting thing, is the ground risk assessment service. So what this means is this vehicle cannot fly on a school area, basically, because schools have a lot of children which are maybe playing on the ground. So you have to avoid that area. So the GRASP actually gives you information about, okay, what is my ground risk assessment service providing to you. It could also be that, okay, you are at lunchtime and there is a lot of people who are outside eating because during lunchtime. So probably from 12 o'clock to 1 o'clock in your main downtown area. So probably I should not fly during that period of time, because it's a possibility that if something happens to the vehicle and it may need to land, probably you cannot evacuate that many people away from it. So those kind of systems. So these systems are providing all the information to the airspace or to the main vehicle system, that these are the constraints and you have to move around it. So our work is mostly on this first part. That's what we have been working. Our partners have been working on the other parts, the GRASP and the weather and everything. But we have been working on the battery prognostics work. We have done a lot of work on the PTT, which is the proximity to threat. Proximity to threat is what? Am I close to a large building? Am I close to a large tree? Why am I close? Why I need to measure that? Because if I'm very close to a building, the wind gust may push me out or it may push me in during my flight path. So if I'm moving forward and if I'm very close to the building, a wind gust may push me directly and I may hit a tall building or something around it. If I'm away from it, probably I may be hitting some other building around it. So I need to know that how far I need to be, or the vehicle needs to be from that building. So those are very interesting things which we have to figure out. But that's what we are trying to do, that everything works in the system. Everything is trying to make sure that you are keeping the vehicle safe and trying to avoid any accidents around it. So with that, overall architecture what we have. So this architecture is what we have been working for the last 4 or 5 years and trying to add each element to it. We work on certain algorithms. We try to integrate those algorithms and then provide that information to the vehicle to keep it as safe as possible. But when we do that, we also have to make sure that when I see something is failing or something is going to happen in the next couple of minutes, if it's within a couple of minutes or seconds, probably a human intervention would not be a good way to do it, because that decision has to be taken at a very short period of time. So probably in that case, autonomy is the best thing to do. So autonomy is like the system has to have an onboard machine learning capability, or a machine or a decision-making capability. It can say, okay, this is the problem. Okay, I have a couple of seconds to make a decision on that. Machine will take that decision that, okay, land the vehicle or keep moving ahead. I don't know what's going to happen, but that's the decision based on its prior known knowledge of the system. What is that known knowledge? This is that known knowledge. So I know that there is some failure in my battery, but taking into consideration all these other information, what should I do? The system can do it on the fly. Probably it may be a not an efficient decision, but it could be a more safer decision. So that's what it will try to do. So, but if it's within minutes or couple of hours, then probably a human, like a pilot or an air traffic controller, can take that decision. Something which is more down the line, like couple of hours or days or minutes. So that's like a maintenance type of work. Basically saying that, okay, probably my motor is not working well. I need to replace it, or I need to re-characterize the motor which is on that UAV or that system. So that's a longer duration goal. So it doesn't need to stop the vehicle at any point of time. It still keeps on working, probably not efficiently. So in that case, you can do that once the vehicle lands and make sure that everything is working before your next flight. So this is how the story is building now. Like you had a very big picture. We then came down to a single vehicle, and now we are moving towards, okay, what the health of the vehicle is, and that's where we come to. And for that comes the understanding of how the algorithms work, or what is our framework. So the framework, what we do is a very basic framework. What it does is you have all your sensors. So it's like a system modeling. So you have your system which receives your inputs. It produces certain outputs. It keeps on looking for, okay, what is the fault? Is there a fault in the system, or is there a fault or it's everything is nominal? If everything is nominal, then the difference between the two, this F would be close to 0, because nothing is there is nothing wrong on the system itself. But if something is wrong, so if your system is providing something X value, and then if your fault, the sensor is providing some other value, then there is a fault in the system. So that means the fault is detected. Then what we try to do is we try to estimate what that fault is. So we are understanding, okay, if there is a fault in the system, is it a high magnitude fault or a low magnitude fault? Once you estimate that, so for that, if you are aware of something like a Kalman filter or a particle filter, what it tries to do is it tries to do some estimates of, okay, where I am, or where my current state is, and based on that, then it will try to predict. It will say, okay, once I know that I have identified the active damage mechanism, then I will estimate it based on my current state, and then I'll try to predict it. So prediction is, okay, I know there is some fault in my system. How much time it's going to take me to actually the system not working at all? So for example, if you have your phone battery, if you have your phone in the morning when you charge it, it's 100%, but at some point of time it will tell you that, okay, only 10%, 15% is remaining, 10% is remaining, and then slowly it will stop working, or it will I think most of the phones will do that. If it starts heating up, it will stop connecting to Wi-Fi, or it will stop connecting to show some of your apps which require a lot of power. So exactly this is what it does, is like it's trying to figure out that, okay, what should I shut down first? And then it gives, okay, you have now 10 minutes left, you either charge or my phone is going to die off. But for the phone, it's fine because the phone sits there. But if it's a flying vehicle, you have to be very accurate. So that's where we come in, where we develop our algorithms which are very precise. They can give you very accurate information, saying that, okay, for the pilot that, or the autonomous system, that, okay, you have only 50% state of charge left in your battery, you have to land the vehicle, or you should not just land the vehicle, but it can say, okay, you can go for the next vertiport or the next airport. It will take you 15 minutes to go there. It will deplete your battery by 15%, which is good enough because you will still land with 35% of charge left in you. So that is the accuracy what we require for, and that's what we strive towards, that whenever we build these algorithms, they have to be very accurate enough that they give you precise information based on which you can take those specific decisions. And how do we do that? We have been looking into developing this physics-based model. So all the models what we do, they are based on an underlying physics, wherein we understand that how that system works. we modeled the damage propagation models. So because a system, if you take one system, or like if you take a battery can get degraded by several things, like it can age over the period of time, or if there is a fault in the battery may start discharging very fast. On the opposite side, what happens is, if you have a motor connected to a battery, if the resistance of the motor trolley increases, it's going to drain a lot of current through the battery. So the battery is going to deplete very fast. But that's not a problem of the battery, but that's a problem of a motor. But the system has to understand that. The system has to know that, okay, it's not a battery fault, but it's a motor fault. And how do you do that? So that's where modeling comes into picture, that I'm running at a very specific RPM, but still there is a lot of current which is being drawn. Why is that happening? That may happen only due to certain cases. Probably it's like one of the case would be that a resistance has increased, and that's exactly what we are trying to do. Like, how do you model that physical damage propagation using a physics model, and then determine the end of life. We develop an algorithms that how can that be propagated forward, and dealing with uncertainty. Uncertainty is always there. What is uncertainty? Uncertainty is, oh, I know there is some issue happening, but I'm not very sure. I'm 50% sure, 50% not sure. So 50-50 is not a good way to do it. And also, when I measure the sensor value keeps on going up and down. Most of you must have done in your lab also, like if I say 5 volts, it's always 5.05 or 4.95 or something. So there is always an uncertainty around it. So we have to incorporate that. And when I also predict something in the future, I don't know what's going to happen in the future. I know my model is good, but I don't know is it going to be 15 minutes, or is it going to be 35 minutes, or is it going to be 1 hour? I don't know that. It's exactly like when a doctor says, oh, you will get better in 2 to 3 days. But that's a good indication, 2 to 3 days. But if the doctor says, okay, you will get better in 2 to 60 days, that's not a good indication, because then that's a lot of uncertainty, right? Like, you can get better on the second day, or you can get better on the 60th day. So that's a long, uncertain period of time. But if the doctor says, okay, 2 to 3 days, that's good enough, that it's within a couple of hours. That's exactly what uncertainty is. But how do you deal with that? Because you don't know what's going to happen in the future. Probably it's something like, if the doctor says 2 to 3 days, and then suddenly you are walking down the road and you hit something, and again you fall sick. So you don't know what the future is going to happen. That's exactly what happens with these kind of systems, that you don't know how the future loading is going to happen. So you give an estimate and then say, okay, probably my vehicle needs 15 to 20 minutes before it should land for sure. So you take that plus minus percentage, and that's where you say, okay, if I'm within plus minus 5%, very good. If I'm within plus minus 10%, it's still good. But if I say that, okay, my vehicle is going to go down on the charge of the battery within plus minus 1 hour, that's not a good information, because then how does the pilot estimate that, oh, should I land here, or should I land like 1 hour later? And if it's between those 2 points, the vehicle may fall down actually. So that's not a good thing. So those are the things, that's what uncertainty does. So you have to be very precise on those parts. So physics is one way, but then there are other ways also. You must have, a lot of you are aware of the physics models, so you must have looked into the physics laws. So the physics, the law of conservation of mass and momentum. Some models are very high fidelity models, so they are complex, so you have to develop these models. So it takes some time. You have to do a lot of experiment. You can take some field data, but you need to do a lot of experiments to get those models. You cannot just come up with those models, because they need to be validated, and they need to make sure that they are precise enough. But in addition to that, in parallel, you can have a lot of data. And with now a lot of IoT work and a lot of work being done in the machine learning, you can develop some models around it. So why don't we use those models? Yes, of course, you can use those models, but there are always limitations on those models, because you don't get all the information. You only get some part of the information, because when the machine is working normally, you can collect all the data. but that abnormality happens only once in a while. It doesn't happen all the time. So models are good, data-driven models are good enough. Sorry, I just doing something. So data-driven models or machine learning models are good till the data coming to you is good data. But the moment the data is absurd or it's not behaving properly, then you have to rely on these physics-based models. But over the period of time, what we came up with was, okay, can we learn some machine learning models using the physics part of it? So that's where we came up with this methodology, and now it's being used most of the time. And you must have heard about this concept called the physics informed neural nets. What it does is it takes in data which is coming from the model, which is the physics model, but it learns some very few parameters of the physics part of it, and it can be learned during PyTorch, or you can use TensorFlow. We have been using TensorFlow and PyTorch for a long time, so that's what we are comfortable with. But you are open to use any other thing. And then once you know that, then you are putting your understanding and learning the physics part of the complex system. So you don't need to know the whole system itself. So you can provide some data information to this machine learning model based on your data acquisition, and you can use that model to learn some physical part of it. So for example, in case of our batteries, what we do is we have a lot of discharge curves for the batteries, and I think, yeah, I'll show that part to you. And so we can learn from that discharge curves. We use a very basic differential model, but differential equation model, but there are some parameters which is like a resistance of the battery or the capacity of the battery. Those parameters we learn it from the machine learning or the data part of it, because we have a lot of discharge curves. We can then convert back them to the understanding those specific parameters and how they change over the period of time. And there are a lot of papers we have written. We started this work in 2018, and now there is physics informed neural nets has exploded like anything. It's a lot of people use it, and it has its own pros and cons, but we have successfully used that in several of our projects. So that's some of the application or the framework what we have. So the framework for fall detection, prognostics, we do the modeling, and then you can also combine that with the physics informed neural net, where you're combining physics model with a data driven model. So how do you do diagnostics? So for diagnostics, you need to know what are my fault profiles. So if I take a UAM, so this was some of the work what we did a couple of 2 years back. So what we have is, if you take a UAM, you have different systems in that. You have avionics systems, you have structures, you have actuators, and then you have the powertrain. Powertrain is what? The one which actually powers your battery, your speed controllers, and your motors, which are actually powering the UAM. So the propellers, what you see on the top, that's what the UAM powertrain is looking like. So then once you have that, you look at the FEMICA, and then you come up with, okay, what are the components? What are the different failures you can look at? For those failures, what are the root causes? And then what effect it has on the UAV. So for example, if a battery pack is having a state of charge failure, the root cause is going to be operational condition. What is the root cause? Operational condition is, I'm flying a certain route, my battery will keep on discharging. And then what is the effect on the airspace? So if there is some issue with the battery, I will need to land the vehicle as soon as possible. And you saw in that big picture when we were flying that blue vehicle or the blue aircraft, whenever there was a failure in that vehicle, you had to change to that red path or any alternative red path. This is exactly where this comes into picture, that if there is some issue on the system, then in that case, you will have to make sure that the vehicle is following a certain path and then landing it. What is the severity? It's a high severity. What is the probability of occurrence? Which is very high. Why high? Because every time you fly, your battery are going to discharge. So you will face that problem each and every time, but it depends on if it's a failure or it's a nominal operation. Is it safety critical? Yes, because you need to keep flying till the vehicle touches ground. So that is very safety critical. So in that way, we come up with the failure analysis model for each component or each system, and then work on it towards it. Once we have this, then we come up with our FEMICA or the Bayesian network. What is a Bayesian network? A Bayesian network is a framework wherein you assign probabilities that, okay, if my state of charge is low, why would that, how can I detect it? So these blue ones are the current of the battery. This is the temperature of the battery. This is the voltage of the battery. Then PM stands for the motor parameters, sensors, and then TE is for the PWM or the what you can say, the speed controllers. So the PWMs which are controlling the motors. So this is the sensing part. These are the failures, and then these are the root causes. So what is the root cause? A state of charge will happen. So whenever the current goes high, my state of charge is going to low. And then why would this happen? Because of my flight profile, or it could be due to some other issue. But then we can assign different probabilities. Now the state of charge, state of health, there is some bearing fault, and there is some winding resistance fault. All of these are related to a flight profile. So you can actually assign different probabilities to them. So you can assign what is my probability that I may land here, or I may land here, or I may land here. That depends on what my probability is, sorry. And what it does is, now if I say, okay, my voltage is low, so voltage low may happen to, my state of charge going low may happen to three different things. It could be this voltage going low, either the motor voltage going low, or the EMF voltage going low. And based on my probability distribution, so the anomaly is that the anomalous voltage reading shows that either VB is 1, or VE is 1, or VM is 1. So the fault could be in either three of them. So depending on my low state of charge, the fault could be either of these three. But then my probability distribution says that, okay, my Bayesian probability says that the state of charge going 1 is high because of these three. So this is high. So that means my probability is very much either of these three voltages going high. That means my state of charge is basically low. So that is the fault in the system. So that's the reason this has the highest probability, and then all the other probabilities, if you see, they're like 0.005, 0.04, which is probably, you can discard them. So these are the top three what probabilities I get, and then among these three, this is the highest probability. Why? Because the winding resistance of the motor, that is not faulty, it's still healthy. That means this is crossed out. My battery is very healthy, so that means the state of health of the battery is high. So that means this is crossed out. So my only remaining option is now this, which is saying that, okay, the state of charge is high. Why? Because I'm flying at a certain profile, and because of that, my state of charge has gone low, which is correct, which is actually exactly what is happening. So this is how probability works, and we are trying to find out that, okay, based on all these options, what we saw in the table, my probability distribution of different sensors, and also my root causes, I come up with this solution. And you can do it for each one of them now. Now you can do it for the state of charge, you can do it for the MOSFETs or the PWMs, you can do it for the motors, and then it becomes a large structure basically. So moment your sensor detects something incorrect, you are able to then make sure that what my fault is, and so you're detecting that there is some anomalous voltage here, but then you're also isolating that which one of that is the actual fault. So you cannot just say, okay, I'm not feeling well. You should the doctor should also detect that, okay, which part of your body is not feeling well. Is it you have a throat infection, you have a nose infection, you have an eye infection? That's exactly what we are trying to figure out, that okay, there is something wrong with the system, but what exactly is wrong with the system? You come up with this probability detection, and what, based on what? Your sensor readings. So that's what the fault detection part is. And now we go to prognostics. Now I know that, okay, something is wrong, I need to take a decision, but how much time do I have? And that's where we come to the prognostics part. So this is where we are trying to say, okay, there is something fault in the system. How much time do I have to land the vehicle? So that can be 5 minutes, that can be 15 minutes, that can be 20 minutes. And what we have is, again, we come to the next part, which is the modeling part. So we have our physics-informed neural architecture. So this is a physics-informed neural net. What it does is it's using a recurrent neural network, which is modified to incorporate information from the system model at an internal state. So this part is the actual differential equations. So these are all the differential equations for a battery. The input is a current, which is the sensing input. So you sense that the input current through the sensor. And then the top model, this is a neural net. This is basically a multi-layer perception layer for a multi-layer perception for a neural net. So this recurrent neural network takes in current as an input variable, and then the cell will be recurrently used for updating both two parameters. So one, if you look at the top, this is the R, which is the internal resistance, and then this is the Q max, which is the number of ions which are present in a cell. So it actually looks at all of this information at the cell level, and then able to make a prediction that, okay, how much charge do I have left in the system? And how does it do it? So this is exactly how it does it. So you have this discharge profile. So this is basically your voltage. The moment you start drawing current, the voltage is going to change. So the black line, what you see, that is actual measurement voltage, which is the sensor voltage, what you see. So that is what you are reading on the sensor. This is the observation only. So the blue line, what you see, those are the observation. And then what we are trying to do is we are trying to use this third part, which is observation plus fleet prior. So what is the fleet prior? So that's where we are combining information from all the different cells. So in this experiment, what we did was we had 8 different cells which were discharging at a certain rate. All of them were doing a very similar flight profile. So all of them were doing a very same flight profile, but we combined all that information together using a machine learning approach, exactly the machine learning framework, which is this framework. So you have the model, and all the inputs parameters were updated using this MLP architecture. And that gave us that, okay, if you fuse all that information, you're able to get that, okay, how the voltage would actually have moved. So if you see, initially there is a lot of uncertainty. So this variation, what you see, that's the uncertainty. That means the model is not very sure what's going to happen. And this is very early in the life of the cell. So this is very like the cell just started discharging, and then you are trying to make an estimate. So the cell says, oh, my uncertainty is very large. Why? Because I don't know how the system is going to behave in the future. So this was when it grew like 0.5 kilowatt hour, which is like very new. But then as the cell started getting more information, so as the machine learning model looked at more information, my uncertainty bounds have decreased now. So if you look at this, my uncertainty bounds have started decreasing. And then when we were close to like 2.25 kilowatt hour of energy being drawn from the battery, we were very accurate. So this is where we are actually predicting. So the black line, what you see is the measurement, and then the blue and the greens, what you see, those are the estimates from the model itself. So that means the model is so accurate enough that it's able to make a prediction that if you just provide a current value to it, it's going to say, okay, based on that, this is how the system is going to behave. So the model is able to predict that how the system is going to behave based on all the information it has learned through these different stages, and also its original physics-based model. So this shows that you can learn the model over the period of time, and that's what we are talking about. Like machine learning takes some time to learn. So we were able to learn very well the model, and now in the future, if you just give the current value to the model, it is able to give you a good prediction. And why this is helpful? So now you can use this model and then give, prior to you taking a flight, you can say, okay, this is my flight profile. This is the amount of current which would be drawn during this flight profile. Will I be able to complete the mission? And if the algorithm says, yes, you will be able to complete the mission, you make that flight. So that is the decision you can take now, that okay, I am very confident that the flight what I'm going to take is going to be completed. You never know, this is just one condition, that okay, given my flight path, I'll be able to complete it, but in between there would be wind or there could be some other issues which may happen. That's completely off, and the model will take care of that. So model will keep you giving that information. But before you take the flight, the confidence level what the operator has is that okay, yes, I can do it, and let's fly it. So this is very useful when you're doing such kind of activities, and especially when you're flying in this complex area. That's what is very much required. So in-time monitor assessment and mitigation capability is very much required to prioritize any hazard in the emerging operation. How do we do that? So we use predictive monitoring assessment which are developed in collaboration with our different partners and within the ISMS context. What is the impact? The technology transferred to external partners made operations safer, more efficient. We are trying to make it more cost effective while providing safety. And to facilitate what the FAA is looking, the Federal Aviation Authority, what are they doing for? The technology will be leveraged by all the different entities, what are there, and also invest in solutions to enable this airborne sciences program mission. So what we are trying to do is we are trying to keep this as safe as possible, and make sure that in the future when you have these complex vehicles which are moving around, trying to keep the airspace safe. But this is all fundamental research. So this is all very basic research. But then at the top, if you look at it, we started from the very basics. So if you look, we went from top to bottom, and the reason for that was to understand that why we are doing these things. So why are we are motivated to do this work, and the reason for that is yes. All the small work what you do, or all the fundamental work what you do, it can be extracted at a very high level. So this is a very high level approach what you see. But if you look at it, we started with like a very basic differential equation. We started with a very basic data driven model or a machine learning model, but which is applied to an actual operating airspace. So that's the depth what we go to. Like we start with very basics, but it takes you to making sure that the airspace operation or the airspace is kept safe. So that's what we strive towards, and making sure that everything works perfectly as more efficient and safe as possible. So in the future, what we are trying to do is also, can you predict the weather? Can you predict the traffic collisions? Or can you look at how the GPS degradation is happening? So these are some other areas what we are trying to look in. I just talked about one vehicle part of it because that's my area of work, which I've been working for a long time. But there are some other areas which also require that same requirement, like traffic collision. That in the future, like if I'm moving in a specific waypoint, is there in the future some vehicle which is going to hit it? Probably it's like 2 seconds later, 2 seconds earlier. Should I take that path? So those kind of things are also important. So there is a lot of work being done on traffic predictions or traffic collision course. There's a lot of work being done on GPS degradation, and that's a new area of research. But in our case, we have been working very much focused on the vehicle health, battery health, system health. That's what we have been trying to focus on. Just to give you a brief overview, that all the work what we do is open source. So all the data sets what I have, they have been open sourced on our website. So you can go to the website, you can download it. Even the algorithms what we have developed, they are open sourced. I think I forgot to add the slide to that, but I should add the slide actually. So our software is called ProgPy. So ProgPy is the software what we have developed in the past several years, and we won the best NASA software of the year award last year. So we are the 2024 winners for that software because of its capability that anyone can use it. Anyone is used. It's free to download. The models are free to download. All the data what you see, the link here, they are free to download. So if something of this area interests you, please go ahead, download the software, download the ProcPy tool and use it. Just test it out and then see if something spikes your interest. So with that, I'll end my talk, and I really am thankful to. So this is not my work. It's an individual. It's not an individual effort. It's basically the group effort. What we have been doing, thanks to my partners at NASA Ames, and also my wonderful SWS team and the NASA Langley Research Center, which is in Virginia. So Patrick Koach and his team, I really work with them, and I've been working with them for more than 10, 12 years now. So thanks a lot, and thank you for the opportunity, Sammy, and the society in your university.
Thank you very much, Mr. Chetan, for this really insightful session. I didn't even know that there's a field that dives into all of these while keeping everything simple enough for our students to understand. We really appreciate the visuals and everything. And of course, thank you for your time. We will be taking questions now
Sure.
from the chats.
Yeah.
And if anyone wants to ask the question, they can raise their hands. Yes, Mr. Raji, you can ask as many questions as you want. We will have 15 minutes to 30 minutes for all the questions. Mr. Chetan, would you prefer if I read the questions for you, or do you
Oh
want
yeah,
to
sure,
read
sure.
them yourself?
Yeah, I was trying to find out.
Okay, Mr. Wajih Al Taif asked, in aerospace systems where microchips have strict limitation on storage capacity, can we ensure robust cybersecurity while prioritizing embedding only the most critical operation commands? And what are the best practices or architectures in both and security without exceeding the hardware constraints? So this question is in the Google Meet chat if you want to read it again.
Yeah. I was able to find it. So yes, Vajif, that's a very logical question, and I think a very important question also. That there is limitation on how much data can be stored on the systems. So especially when you are working on the small vehicles, they are always limited by capacity. So in that case, what happens is the new way, what they are trying to do is they not keeping the data on board, but offloading the data. So there is always a secured connection with a downlink. So there is work which has been going on wherein they are trying to offload the data through their service providers. And I think that's one of the links what I showed also. That's exactly what it does. So if you look in here, that's what they try to do. So they have this bus, and on this bus all the information is stored on the bus, or on the service provider's bus. So if the vehicle gets some information, it downloads it or it offloads it to this bus, which is a ground station, and this ground station may be connected with a Wi-Fi or a 5G connection sort of thing, wherein they can offload all the data, which is as much as possible. So there is a lot of security confirmation there. So there is a lot of security where we can make sure that once the secured connection is done, that's only when the data is downloaded. So there are some aspects to that. So hopefully that's the first part of it. And the second part is making sure that the security or hardware constraints are there, because you should be constrained on how much power is being drawn, especially when you have small vehicles. We have started looking into some neural nets which can run on board, but which take very low power, which can give you some diagnostics information. So yes, there is constraint on how much load you can take. And the other part what we also look into is when you run these systems, we test it on different hardware locally also. So making sure that we are not using very high power devices, which may draw in a lot of power from the computational point of view also, and from the computation, the power point of view, wherein it's not very draining your batteries itself when the vehicle is flying. Hopefully that answers your question. And I see another question, which is introducing new security challenges. This is the project on which I'm actually working. Security routing protocols to exchange sensitive data in secure environment. Absolutely right. Yes. So that brings in more challenges, which is absolutely right. And I'm very good that you have looked into this. So that's a very key part of the work wherein all your data is on a secured line and also on a secured system wherein the data is not leaked out. And the eVTOL work, what they have been talking about, that's exactly what they're going to do. That there would be a one-to-one P2P protocol or P2P line wherein you dump your data on a secured line on this bus, and that bus would be a secured bus wherein the data could be exchanged then. But I'm very happy that you are working on it, and this is one of the key things to look into. Absolutely. Yes. Uh, okay, I may not be able to answer that question. So Vajid is asking, what are the key cybersecurity challenges faced by radar systems in avionics, particularly within the context of military applications? Unfortunately, Wajif, I'm not an expert in that, so I can look into that and I can respond to you for sure. But I have not looked into those systems for a long time. Okay, so
So,
and
Mr.
then
Chetan, if there are any questions you would like to answer after this meeting, you can send me a follow-up email and I can
yes,
broadcast it to all the participants if you
absolutely,
want.
yes, 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 yeah, yeah. So because someone um, like hacking and cyber security is not my area of research, so sorry for that, but I can look into that and I will reach out surely for I know lot of researchers in our group who are in that, so we can surely respond to that part. And I know for so this question, when I gave a talk at the Palo Alto Research Center like 7 or 8 years back, there were researchers working on it that time, so I'm very aware of this area. But sure, Wajif, I'll be happy to look into that and then I'll respond to you. And then there is Muhammad has a hand raised, so go ahead, Muhammad.
So, Mr. Raji actually has one last question. He
Oh
said,
yeah,
in your
okay.
opinion, can we truly rely on AI, or particularly generative AI, not only for automation or autonomous decision making, but also for accurate prognostics in such critical systems today?
Uh, That's very good question, and that's something what I've been working on currently. So what we are trying to do is, yes, generative AI is not currently capable of doing any predictions. They are still limited on that, and also there is a lot of work which has been done on how good the output is, like because a lot of Gen AI they do hallucinate, and they always need very much accurate data. So in that case, still though that's work in progress, but how can you support that validation? So can you validate the outputs which are coming from Gen AI outputs? And that's currently some of the research what I'm doing on, wherein can you look into the validation through sensor outputs or sensor inputs, or through certain models which can support that. So to validate what the Gen AI is saying and what your models are saying, and can you do some validation around it? So those are some of the concepts which are looked into. And yes, you're right that right now we may not 100% work on it or 100% rely on it, because sometimes it may hallucinate, and especially when you are working on complex systems and critical systems, you have to be very conforming, or at least you should be very confident about what the outputs are or what decisions you are allowing the system to take. So yes, it's a research in progress, and I'm very happy that you are looking into those aspects of it. So thanks for the question.
Thank you, Mr. Waji, for your question. We have a question from Muhammad Aziz.
Yes,
Go
go ahead,
ahead and
Mohammed.
open your mic.
Okay, thank you, Mr. Chetan. Actually, my question is very similar to Mr. Wajih's question. I was going to ask about safety. I mean, at higher autonomy levels, how do we ensure that AI decisions remain explainable and
Yes.
trusted, uh, as you said, in safety critical operations?
Yes, absolutely. No, so AI decisions to be acceptable or at least used. There is a lot of validation required. So there is a on top of the AI decision system. So when you have a physics system, you know what the underlying physics is, right? So because you know that okay, if I say a register is not working, probably yes, the I can check and manually do that. So there would be a layer of VNV which would lie on top of the AI decision maker before the decision could be taken. So there would be a in between layer which could be a VNV layer, and that's where we could add in supporting information to it. So if the AI decision maker gives certain output, is it verified? Is it a verified output? Because these outputs are not deterministic; they are stochastic, right? So if I trigger it once, it would give me one output. If I trigger it again, it will not give me the same output with the same input. It will give me something else. So that's where the stochastic systems comes into place. So for that to make a validation, and it's with the same with your if you ask Gemini or your chat GPT, if you have the same question, you may get two different answers. So for that, you need a good validation system on that. So that's where the VNV layer will come in between, and that's where some of the work what we are doing is you get an output from AI system, but you also have a conforming output coming from a valid model or a valid uh, system output, and then you verify it at one level before you can say a decision that okay, this output is correct or not. So that's where the research is going towards, that how to make them more reliable and more approachable from what's going on currently. Because it's not like okay, it's a cat or a dog, right? Like if I give a cat image asking them is it a cat or a dog, it's basically a decision that should I land or not land, which is a completely very different decision than saying that okay, if I see a cat with the stripes or it's a tiger or a lion or whatever that may be. So that validation step is very important. It happens in our case also. Like in our case also, if my model is trying to deviate away from its actual thresholds, I start relying less on the model itself and then trying to rely more on what the sensor outputs are coming or something like that. So those kind of frameworks need to be integrated. So these are two different frameworks which need to be integrated to make AI more viable and more useful in critical systems.
Thank you.
Yeah, and I think
Thank you very much.
both of you are looking into a very good approach. I like this because that's what you're thinking from this perspective. So this is very good from the research community, and also going forward that how do you integrate these AI or Gen models into actually decision making capabilities. So good work on that. So I'm very happy.
Thank you, Aziz, for your question, and thank you, Mr. Shaitan, for your extensive and really simple answer. So I'm glad we actually touched on these points like security and the real issues of AI, even with its limitless possibilities. So if there are any questions from the chat, we would be glad to have them. So if you can raise your hands or write your question in the chat.
And also, if
We'll
there are
give
no
them.
questions today, I'll send Sammy my email address. You can always write to me for any of your questions. I'll be very happy to do that. So don't worry that this is not only the point. We'll go more. Do reach out to me. You can reach through LinkedIn or through my email address, and I'll be very happy to answer the questions.
Okay, then that's perfect. We will. Okay, Mr. Wiji has asked a last question, and in the name of our students, Is there any internship possibility for interested people about the topics that you exposed?
Yes, so NASA does have internship opportunities. I can also send a link for those. It's a bit difficult if it's an international student, but there are NASA Ames especially does have internship opportunities for international students also. So Sami, I'll share that internship opportunity link with you, so you can share it with the students so they can look at those opportunities. And if there is some collaboration research, we also have the capability that in case I'm working with another professor or any professor who is interested and the student want to visit us for a few days or a few weeks, we have that opportunity. So absolutely that could be done. So there's a lot of in between management thing which happen, but yes, we can make it somehow we can work around it. I've worked with a lot of students from Europe and other states, so Canada. So yeah, it's doable.
I think after this session, a lot of people would be working on their research papers about this topic because
Absolutely.
it's obviously a very interesting topic, and it's since the IEEE Instrumentation Society offers this much opportunities like the congresses you mentioned and everything, you should also, if you don't mind, sending the links that you provided from during the first few minutes of our episode.
Yes.
You talked about
Yes.
the society, so we
Yes.
can have a brief summary about that, and we'll send a follow-up to our participants.
Absolutely, I'll do that. I'll actually do that.
Yes, Mr. Raji said we can also involve the IOSS chapter.
Sure, absolutely. Yeah.
So a small teaser for all the participants. We actually have a distinguished lecturer from the IOSS chapter in 7th of August. We will be hosting a distinguished lecture in regards to our theme AI in space. I encourage you, Mr. Chetan, also to attend the other sessions. I'll be sending
Sure.
you invitations to all of them, if of
Absolutely.
course you have the time and everything.
No problem.
And let's wrap this up. Thank you very much, Mr. Chetan. I am very proud and very glad to have this episode with you. You shared a lot, years of knowledge into an hour and a half. You made it interactive. You made it fun. You made it very interesting for us. I appreciate it. Thank you very much.
Yeah, thank you so much for the honor, and thanks everyone for being here. So thank you.
Thank you.
Okay.
Goodbye,
See you.
everyone.
Bye.
Bye-bye.